Good morning, everyone. I hope you are well. Sorry for the absence of videos as my exams and school were going on. Today's topic is Graham's number. This is another big number. To understand it, we first have to know something called the arrow notation, which was invented by Donald Knuth. So first, let's take 3 arrow 3. Now this arrow just basically means 3 to the power of 3, which basically means multiply this number by this number of times. So 3 times 3 times 3, which equals 27. Simple. Now let's take 3 double arrow 3. Wait a minute. So 3 double arrow 3. How much is that? Well, double arrows basically create a string of single arrows this number of times. So since we have 3 double arrow 3, we will take 3 arrow 3 arrow 3. Now we know that what 3 arrow 3 means. So we have 3 to the power of 3 arrow 3. 3 arrow 3 is 27, which comes out to, and 3 to the 27 comes out to be 7.6 trillion. Another way to think about these double arrows is that you are building a tower of this number of times. So in our example of 3 double arrow 3, we do 3 to the power of 3 to the power of 3. And we will work from top to bottom, left to right. Okay? And that's how we get our answer. What about 3 triple arrow 3? Well, similar to how double arrows create a string of single arrows, triple arrows create strings of double arrows. So we have this guy will be 3 double arrow 3 double arrow 3 double arrow 3 double arrow 3. Now 3 double arrow 3 is 7.6 trillion, which means that now 3 arrow 3 is 3 to the power of 3 to the power of 3, so on and so forth, 7.6 trillion times. For comparison, 3 to the power 3 to the power 3 to the power 3 is a number with 3.6 trillion digits. So you can imagine try and imagine how huge this number will be. And remember, this is only 3 arrows. The first rung on Graham's number is 4 arrow 3. Now you can probably guess that this is 3 arrow 3 arrow 3. And we know that 3 arrow 3 is unimaginably big. So what is this saying is that we have, hold on a minute, 3 arrow 27, and it is the number of 3's in this sequence, 3 arrow 3. But this number just tells us the amount of arrows in another tower of 3's below it, like so. However, this number, as you can probably guess, only tells the number of trees in the arrow below it. And we keep on doing this for a long time. How many times? Well, this number, 3 arrow 3, which is extremely big itself, So you can imagine how big this 4-arrow field will be. We'll call this monstrosity, 1 minute, G1. Now you might be asking, is this Graham's number? But actually, it's way smaller than it. What we do now is take 3 arrow, 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 and so on. However, this time, as you can probably see, there are a huge number of arrows. How many arrows? That is 3, 4 arrow, 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 3, or G1. Or G1. And we know how ridiculously large this number is. And we know how arrows can blow things up beyond belief. And now we can't even count the arrows. That escalated quickly. Now let's call this monstrosity G2. Now we're going to take 3 arrow, arrow, arrow and continue doing that. And how many arrows we are going to put between this now? If you say G2, then you are correct. Now this will give us G3. Now we do this entire thing again and again until we reach 3 arrow, arrow, so on, G63 times, which gives us G64. And there we have it, Graham's number. Now you might be wondering, what is the use of a number so big that, well, if you thought about it, your head will collapse into a black hole? Well, it is actually an answer to a simple question involving colorblind. Allow me to demonstrate with the scale. So first, let us say that we have a square. I'm just going to draw a rectangle. It's a stretch out. Now, we have these 4 vertices. And now, that means that we are going to have 6. Now, we are going to draw all possible lines. Now, we'll have 2 different colors. Now we can color this guy one color and this guy a different color and then this guy a different color. We can choose 2 colors, okay? Now the question is there a dimension where the following condition is avoidable? And the following condition is that you cannot have any 4 vertices, any group of 6 or 4 vertices, 6 lines to be red or entirely of one color or entirely of another color, and these can't be out of the 2D plane. For example, they can't be, like a 3D parts of a different thing. No, they have to represent a 2D square. And it happens that in Graham's number dimensions, or G64 dimensions, these 2 configurations are unfortunately not avoidable at all. Now, the answer could be a lot less than Graham's number. In fact, the lower bound is 13 dimensions and the higher bound to the answer is Graham's number. But still, you can probably guess that Graham's number in itself is humongous.